All right, so 12.2, we are talking about the difference between independent events and dependent events when it comes to probability. All right, and here's your definition for independent event. So an independent event is when the occurrence of one does not affect the occurrence of the other. What that means is no matter what happens in the first event, the first thing that we do, that's not going to change the probability of the second thing happening. So it would be like flipping two coins. If I get ahead the first time, that doesn't change the probability of getting ahead a second time. It's always going to be a 50-50 shot, right? It does not affect it. Spinning a spinner, whatever I get the first time does not affect what I get the second time. Okay, those are independent of each other. Okay, flipping a coin, rolling a die, spinning a spinner, all independent things. We'll talk about dependent in a little bit. Dependent is different. It will change depending on what happens the first time around. We're going to concentrate on independent here. The probability of independent events, you don't have to write all the words, just the symbols are fine here. To find the probability of independent events, all we have to do is multiply those two probabilities together. So find the probability of the first thing happening, find the probability of the second thing happening, and multiply them together. That's going to give us the probability that both of them happen. So this is where that number 8 in the homework comes in. Number 8 in the homework, if you remember, said, what's the probability? I've got two decks. What's the probability that I pick a spade out of both of them? Well, the probability of picking a spade out of one is 1/4. There's 4 suits. My card could be one of 4 suits. So I got a 1 in 4 probability that it's a spade. Okay, I put that deck aside. I grab my second deck. I do the same thing. Well, that second one is also a 1/4 probability that I get a spade. The probability that both of them occur, I just multiply those together, and it's a 1/16 probability. A whole lot easier than trying to draw out whatever they wanted you to do in 12. Okay, so we multiply those together. I want you to find the probability that if I flip 4 coins, that all 4 of them are heads. What's the probability that all 4 are going to be heads? So somebody next to you, what's that probability? How do you get it? 1/16. Why did it? All right, what did we? Raise your hand. What did we end up with here? 1/16. All right, that's 1/2 each time. 1/2 probability. So we're looking at again 1/16. Just happens. All right, good. Any questions on independent events here? Okay. Good deal. So let's move on to dependent. Okay, dependent. We've got a couple words here. You don't need to write the whole thing, of course. I would write the last sentence here where it has dependent events on it. And you might want to write the one that's down below as well. I'll give you a minute to copy and then we'll talk about it. All right, so dependent events. The occurrence of one does affect the other. I might have an idea of what this might be like here. Cody?
Like, it was like question 6 in the homework where like, they would draw marbles out of bag, but you don't put them on everything that you draw.
Perfect, yeah, without replacement, it's that key phrase is without replacement, or we do replace, or we don't replace, right? It's always, do we put the thing back in or not? For some reason, in math class with probability, we always like bags of marbles. Okay, there's always bags of marbles, always. It's like measuring trees, we always do that too. Right?
With cardboard boxes.
Yeah, of course. It's easier. Right? So yeah, the bag of marbles, we saw that in the homework, right? After you take one out, if you don't put it back in, that changes the probability the next time. Right? And if it changes the next probability, that makes it dependent. It's dependent on what we did first. So let's say, well, let's get a second color here. Get fancy.
Oh, shoot.
I know it. Here's our bag. Somebody thought this was a fish tank. Kind of looks like it, but.
Oh my God.
I thought it was a lake.
Yeah, that's how I thought about it.
More of an ocean.
Oh yeah, that's like the trends that we do in science for like football.
All right, so here's our
It's like
here's our bag of marbles. Okay, we got 7 marbles in there, 4 blue, 3 red. That is a bag. It's very clearly a bag of marbles.
They're spaced out. They're 6 feet apart.
Very clear.
what's this? It's very small.
You're very good at your
Like that's
Thank you.
You could be an art teacher.
Hey, I will have you know, I got 3rd place in an art thing in 4th grade.
I got first place in kindergarten.
That was my artistic feat. Was in 4th grade. That was the highlight of it. I went to like a whole dinner thing and I got like a 3rd place thing. It was-
Well, I got
like the only thing you remember from work.
that was it. Yeah. And it was an American flag. It was an American flag with a smile in it. Yeah, it was pretty cool. Yeah, I don't know how it did win 1st place. All right, anyway, back to this because I'm filming this and people don't care about that. All right. We want the probability, we want to find the probability that I draw 2 blue marbles here. Okay, 2 blue marbles without putting it back in, so without replacing. So if we do the first one, right, the probability the first time that I pick a blue marble out, what's that going to be? Brody? Not 1 out of 7. 4 out of 7, because there's 4 blue possible, right? So I can pick any one of those 4. My probability of getting a blue marble out is 4 out of 7. Okay, so I take that blue marble out. I don't put it back in. Now I'm here. What's the probability now, my second time, that I take a blue marble out? Oh, 3 out of 6. Okay, you have to change that denominator. If it's a dependent event, that means it's changing the probability. We have to change that denominator with it. Okay, that's the #1 common mistake, is to try to keep a 7. Now I only have 6 left. Hopefully visually we can see that, right? A little bit easier. When we do this, we have to assume that we got what we wanted. Okay, so when we start finding that probability of that second thing, we have to assume we found the blue the first time. And then we took that blue out. So there's 1 less blue in there. There's 1 less total, 3 out of 6. We would multiply those together and we would get our probability. We would simplify it. So feel free, you can multiply and get 12/42 and then simplify that. You can simplify it ahead of time, right? You can simplify the 3/6 into 1/2. You could simplify the 4 and the 2 and get that 2 7s. Or, right, we can multiply, get 12/42, divide top and bottom by 6, but it does have to be simplified. Right? Yeah.
You can also just put it in the calculator instead of using the division symbol, use the ABC symbol.
You could. Or, you know, you could trust your math abilities.
I'm just trying.
Anyway, all right, any questions on that? dependent events here. Okay, the other thing here, conditional probability. Conditional probability is just the second part here. It's that second probability that we did where we got the 3/6. That's what we're looking at here. This would be the probability if we were using this in our situation. It would be what's the probability of getting a blue when I already picked a blue? So what's after the bar is what's already happened. It's what happened the first time. Okay, that's why it's conditional. It's conditional based on something already having happened. So this is the probability that I got that B happens if A has already occurred. Okay, that's our conditional probability. So when you see it with that bar, that means whatever's after the bar, that has already occurred. That has to be true already. And then we want the probability of the first thing happening now. Okay. That can be a little confusing sometimes, but we'll see it again tomorrow. Okay, so we can work through it. Okay. All right. It's okay. I think my mom still has the original. It'll be okay.
You should bring it in.
It's really not good.
There's a spot on your wall.
Third place.
I'm gonna go look at your mom's Facebook.
What happened? If you added 2 eyes, it would have gone first. If it had eyes, it would have gone first.
Yeah,
It
it's
would have
not
been
like,
like my
Hey, since we did the independent, let's copy this down for dependent. All right, the symbols. Let's get this down. Okay, so this is dependent now, and you see that conditional probability for that second one. The conditional probability. Right?
What does that line mean again in the middle?
This,
Yeah.
that's our conditional probability. This is saying the probability that B is going to happen, given that A has already happened.
Did we learn that?
I just talked about.
yeah, the flag
It's
on.
still
Go
up
back
on
and
the
watch the
board.
video.
Still up there.
Still up on the board.
Oh, all the way.
Yeah. All right, where we at? Bummer, watch the video, go copy it down there. All right, so here's our real world situation. Somebody has a bag of $21 bills and $500 bills. You take one out, obviously you're not gonna put the money back in, right? You're gonna take the money, you're gonna keep the money. Right.
Well, we're Mr. Beast.
Anyway, so we want to know what's the probability that we're getting $200 out of this. Okay, talk to somebody, figure it out. What's the probability we're getting $200 if we only take 2 bills out?
There's 25 bills.
So.
That's where.
No, those are like.
Mr. Gnosky, you know that Iowa's beating, I mean, it's like getting crushed by Oregon?
Well, see, I'm paying attention to math. But yes, I do.
I know, right?
I was watching it.
All right, hey, here we go. Here we go. What's the probability that that first bill is $100? Probability that's the first one. Cool.
1 out of 5.
1 out of 5, right? That's $500 bills out of 25 total. So you got a 1 in 5 chance that that first bill is going to be $100.
That's really good news.
Okay, what about, we're doing a lot of talking. What's that probability that the second one? So I already picked $100 bill out. What's the probability that the second one is also going to be? 4/24. Right, 4/24, or we simplify that down to 1/6. So we multiply those two together, that's gonna give me the total probability of getting that that $200 out of this, which is 1 out of 30. You got a 1/30th chance to get $200,
Easy.
which is about 3.3%. So not great, but it's still money. Right? All right. Here's our next one. We got this one, we got one more. All right. Here's our next one. We got we're taking 3 cards out of a standard 52 card deck. We want to know what's the probability that all 3 cards that we take out are hearts. 2 different situations. One, when we replace the card every time. So it's a brand new deck every time, because we put it back in. Or B, we do not replace it. We take that heart out and keep it out. We want to know the probabilities for both of those situations. Okay, feel free to talk to somebody about it. Let's figure out those probabilities.
Yeah, because during this intermission break, make sure to like, subscribe. I should like put this up on my.
Oh.
For one over four. And then don't put it back. Yeah.
Okay. Still.
No.
164.
There you go. 13.
Wait, so there's 13 of each color card? Oh, yeah.
Of each suit, yeah.
Like that.
13.
We don't really need 3.
Okay. And that'd be 12 out of, that'd be 12 out of 15.
Go ahead. All right, first situation, we're replacing it every time, we're putting it back in. What's that probability that we're gonna get all 3 hearts when we replace the card every time? Brody? Golden? 1 out of 64. Because each time you got a 1 in 4 chance, right? A 1 in 4 chance that you're gonna pick that heart. Multiply those together, get 1 out of 64. That's gonna give you about 0.16 or about 1.6%. And 1.6% chance that we're gonna take all 3 hearts out. Now for B, we do not replace. That first time is gonna be 13 out of 52. It's a 1/4 chance. There's 13 of each suit. There's 13 out of 52 that first time. We don't replace it. What's that next one going to be here? Back
12 out over 51.
12 out of 51, right? Because we took that heart out. So now we have 1 less heart. We have 1 less total. Same thing as we go that third time, 11 out of 50. So we're going down the line every time here. We have to assume that we got that heart every single time that we're trying. And that's what we're trying to find is that probability. So we multiply all of these together. We're going to end up with about 0.013 or about 1.3%. So it's pretty close, right? But definitely a better chance if we do replace it. Okay. All right, questions on that before we look at our last thing? Last thing that we're looking at, I want you to copy this down right here. And then we'll talk through a problem that uses it. P is probability. It's the probability of what happens in the parentheses. All right, so A and B are different events. So like this is the probability that A occurs.
Okay.
So just pointing out what all these things are, right? Probability that A occurs, this is the probability that both things occur. And this is that conditional probability. This is the probability that B happens, assuming A has already happened.
What's that little line?
That just tells us that it's a conditional probability. Maybe you guys should concentrate less on basketball games and more on what I say, so I don't have to say it.
Hey, Bertie.
Because that's the third time I've explained that. At least the third time I've explained what that is.
Yeah.
At least everyone in the
I
team will
do.
know. What was it again?
He asked that.
Why does he say that?
All right, here we go. So here's our situation, okay? Here's our problem. We're gonna use that equation. We're also gonna talk it through logically. But it says at a school, 60% of students buy a school lunch. That's A, is buying school lunch. 10% of students buy lunch and dessert. That's A and B happening. Right? 10% is lunch and dessert. We want to know the conditional probability. We want to know what is the probability that a student who buys lunch also buys dessert. So assuming that they have bought lunch, what's the probability that they're also going to get dessert? That's what this question is asking. So if we use that equation, we're looking for the probability of dessert, given that they've already bought lunch. We can take the probability that they do both, which is 10%, and divide it by the probability just of A happening, which is they bought a lunch, which was 60%. So we do 10 divided, you can drop the percent, you can change them into decimals, however you want to think about it. This is just 10 divided by 60, which is 1/6, or about what, 16%, 17%, something like that.
What? I think it's 6, 7.
About 17, right? So that would give us the answer to that. Now, we can also think of this logically, right? If we drop the percent and just think about it as numbers, sometimes it's easier for us to understand. Right? If we drop the percent. So at a school, 60 students buy a school lunch, 10 students buy both. What's the probability that a student who buys lunch also buys dessert? So the total number of people we're talking about right now is 60. Because there's 60 total that have bought lunch, and we're only talking about the student who buys lunch. Out of those 60, 10 of them also got dessert. So we can logic our way through it. I think I just invented a verb. But we can logic our way through it. Works for me. And get there, or we can use that formula, that equation. Okay, whatever's going to work for us. All right, any questions? Independent, dependent? All right, go ahead.